What specific problem does the new method aim to solve?
The new method aims to solve the problem of defending against adversarial attacks on language model alignment. Specifically, the method focuses on ensuring the safety of model outputs by introducing a defense mechanism using self-evaluation. This defense method aims to classify inputs and outputs as safe or unsafe without the need for additional fine-tuning, thereby reducing the susceptibility of models to attacks that can generate harmful outputs. By decoupling safety classification from generation, the defense becomes challenging to attack in adaptive settings, providing a robust solution to the growing number of attacks observed against existing defenses. The goal is to achieve high accuracy in classifying inputs and outputs as unsafe, particularly when they contain adversarial suffixes, outperforming other defense methods and commercial moderation APIs.
How does the proposed method work, and illustrate it step by step?
The proposed method works by utilizing model self-evaluation as a defense against adversarial attacks on model alignment. The defense involves a model E evaluating a combination of generator input X and output Y to classify it as harmful or not harmful. If the content is deemed harmful, the chatbot pipeline will generate a refusal to answer, ensuring safety. The defense operates in three settings: input-only, output-only, and input-output I/O. In the input-only setting, E evaluates only the user prompt X, preventing harmful prompts from reaching the generator. In the output-only setting, E evaluates the generated response Y, discarding harmful outputs. In the input-output setting, E evaluates both the prompt and output, providing the most context for determining harm. The defense is evaluated under different attack settings, including input with adversarial suffixes appended. Results show that the defense significantly reduces the adversarial success rate, ASR, compared to undefended generators, bringing the ASR to near zero. Zero for all evaluators and settings. The defense outperforms existing methods like LlamaGuard 2 and commercial moderation APIs, demonstrating high effectiveness. The defense is also resistant to adaptive attacks, where the evaluator is targeted separately. Even when attacked, the self-evaluation defense maintains a higher level of defense than an undefended generator. The method is practical, easy to implement, and achieves higher performance than commercial moderation APIs and LlamaGuard 2, making it a robust defense strategy against adversarial attacks on model alignment.
What are the theoretical or practical benefits of using this method?
The theoretical and practical benefits of using the self-evaluation defense method outlined in the paper include 1. High accuracy. The method demonstrates that pre-trained models can classify inputs and outputs as safe or unsafe with high accuracy without the need for additional fine-tuning. This ensures that harmful outputs can be effectively identified and prevented. 2. Cost-effectiveness. The defense method is easy to implement and does not require costly algorithms or fine-tuning, making it a practical and efficient solution for ensuring the safety of model outputs. 3. Robust defense. The self-evaluation defense method outperforms existing defenses, such as LlamaGuard 2 and commercial moderation APIs, particularly in scenarios involving adversarial suffixes. It provides a strong defense against attacks on model alignment. 4. Adaptive attack resistance. The defense is challenging to attack in adaptive settings, as attacking the evaluator would require training a separate adversarial suffix targeted specifically to the evaluator, making it a formidable defense mechanism. 5. Maintaining utility. The defense ensures that safe inputs are not unnecessarily refused, addressing the issue of over-refusal that some current generation models face. This helps maintain the utility of the model while enhancing safety. 6. Comparative performance. The self-evaluation defense method performs on par or better than larger models like GPT-4 with smaller open-source models, making it accessible and effective across different model sizes. 7. Consistent classification. The method consistently classifies attacked inputs as harmful, regardless of the suffix appended, showcasing its reliability in identifying unsafe content. 8. Robustness. Even when attacked, the self-evaluation defense method provides a higher level of defense compared to an undefended generator, demonstrating its robustness against adversarial attacks. 9. Improved model alignment. While adversarial suffixes can bypass generator alignment, the self-evaluation method ensures that the model's ability to classify inputs as harmful remains intact, strengthening the overall alignment of the model. 10. Enhanced defense mechanism. Compared to other existing defense methods, the self-evaluation defense method shows less susceptibility to attacks and provides a more robust defense against adversarial attacks, making it a reliable choice for ensuring the safety of model outputs.
How is the method validated or tested?
The method is validated or tested through a series of evaluations and attacks in different settings. The authors evaluate the defense method in 3 defense settings: input only, output only, and input-output. They test the defense against various attack settings, including input with nothing appended, input with GCG's default initialization suffix, and input with an adversarial suffix trained to target the generating model. The authors use different LLM evaluators, such as Vicuña, 7B_V1, 5 Llama 2, Llama 3, and GPT-4, as well as comparison with LlamaGuard 2 and evaluation APIs provided by Azure, OpenAI, and Perspective. The results are presented based on the AUSR attack success rate for unsafe inputs with adversarial suffixes appended. The authors also consider the impact of the evaluator on safe input performance by measuring the AUSR for safe inputs in different settings. Additionally, the authors design adaptive attacks, such as the direct attack and the copy-paste attack, to test the defenses against adversarial attacks targeting both the generator and the evaluator. Through these evaluations and attacks, the authors demonstrate the effectiveness of their self-evaluation defense method in comparison to existing defenses and APIs, showcasing its robustness and high level of defense against adversarial attacks.
What results were achieved with this new method?
The new method achieved significant results in defending against adversarial attacks on model alignment using self-evaluation. The defense method demonstrated that pre-trained models could classify inputs and outputs as unsafe with high accuracy without the need for additional fine-tuning. The results showed a drastic reduction in the AUSR of inputs attacked with adversarial suffixes, bringing the AUSR to near zero. 0% for all evaluators, generators, and settings. The defense method outperformed existing methods, particularly for samples containing adversarial suffixes, which other defenses often failed to classify as harmful. The self-evaluation defense was challenging to attack in adaptive attack settings, requiring training a separate adversarial suffix targeted to the evaluator. Overall, the defense method provided a higher level of defense than an undefended generator, and was more robust compared to other existing defense methods.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method presented in the paper include the potential extra cost incurred by the output-only defense, as it may lead to the generation of harmful responses by the generator that need to be discarded. Additionally, the input-output defense, while providing the most context for determining harmful outputs, is the most costly in terms of both evaluator and generator resources, as the evaluator must evaluate all tokens in both the input and output. Another drawback is that the defenses presented rely on querying another model, which could introduce latency in the response time of the system. Furthermore, the method may be susceptible to adaptive attacks, as demonstrated by the direct attack and copy-paste attack, which can still lower the AUSR of the defended model, albeit to a lesser extent than an undefended generator. Lastly, the method may not be completely immune to attacks, as shown by the possibility of training a suffix to target both the generator and evaluator simultaneously, though the OSR remains lower than that of an undefended model.